In a previous video, I showed that a current-carrying loop that has a magnetic field cutting through it perpendicularly would feel no net force and no net torque. This is because when we do the right-hand rule on every segment involved in the loop, we see that in these cases, all the forces are directed symmetrically outward, and they would all cancel. But another way to understand why there's no net torque on this loop is to use the magnetic moment of the loop. We can find the magnetic moment direction of a loop by using the right-hand corkscrew rule. The way it works is you would use your fist and you would curl the fingers in the direction of current. In this particular case, what would happen would be the fingers would curl around this way, and it would cause the thumb to point downward if using the right hand. The fingers curl in the direction of the current in the loop. And then the thumb points in the direction of the magnetic moment, which was called mu. Now, in another previous video, I showed that the torque on a loop could be given by mu cross b. Here, since the direction of mu is the same as the direction of b, their cross product is 0. The magnitude of the cross product would be given by mu b sine theta, and the theta is the angle between mu and b. But mu and b are actually pointed in the same direction here. So the theta would be 0, and the sine of theta is also 0. This shows that the net torque on that loop would be 0. However, in this orientation, we see that things are going to be a little different. Here, using the right-hand corkscrew rule, what will happen is the thumb will not point directly down, but it will actually point at an angle. So our mu direction is not parallel or anti-parallel with the B field. Instead, our mu comes out of the plane perpendicularly, like this, and we can find this angle that it makes with the B field using a little bit of geometry. All right, so this is going to be a 30-degree angle here. So the angle between mu and B would actually be 150 degrees. We can see here, according to the formula, that the torque is not going to be 0. So what kind of torque will we have here? One option for finding the direction of torque is actually using the cross product. And we can point our pointer finger in the direction of mu, and our middle finger in the direction of b, and then our thumb will be the direction of torque. It's going to end up being what's called a pseudo vector, though. So it'll point along an axis of rotation rather than an actual direction that any of the particles are going to move. So how does that work? Well, point your pointer finger in the direction of mu. All right, we'll have the middle finger point this direction. There'll be some other fingers. The thumb will actually point back in space here. Okay, so the pointer is mu. The direction of the middle has to be 90 degrees with mu, but toward the way that B is pointing. Basically, it's the component of B that is perpendicular with mu. We see that the thumb now points back in space, and that is actually going to be the direction of torque in this case. So torque, interestingly, is a pseudo vector pointing along the axis of rotation. So that is going to be the direction of torque. So using the pseudo vector of torque, which is along the axis of rotation, we can determine the direction of angular acceleration of this loop. All we have to do is point our thumb in the direction of the pseudo vector, and our fingers will curl in the direction of angular acceleration for our object. That's from Physics 1. All right, so that's our torque direction. The thumb points in the direction of torque, and we see that our fingers are curling in a clockwise fashion. And so that's going to be the angular acceleration of this loop. It'll be clockwise. The torque is clockwise. Or you could say the angular acceleration of the loop is clockwise. All right, that's just one way of finding an answer, but there are others. We could also use the right-hand rules that we had used above on each individual segment. Now let's try to analyze the same problem using the right-hand rule on each individual segment. For this front wire, we would get this. Pointer finger points in the direction of current. Middle finger points in the direction of B. And the force is directed inward. So we would get that. If we do the same thing on this rear segment, we find that that force is going to be directed inward as well. If we do the same analysis on this left wire here, we see that the force is directed inward, but it's actually not going to be toward the center of the loop. Instead, it'll be directed directly to the right. And finally, if we do it on this lower segment, here we see that the force is directed to the left. Now these forces will cancel out so that there's no net force. However, in this situation, there is a net torque. In which direction will the loop want to rotate according to these forces? Well, the middle ones cancel out, but we have a force directed to the left on that bottom wire and a force directed to the right on that top wire. This is going to make our loop want to rotate in a clockwise fashion. So the net torque is clockwise. Or you could say the angular acceleration of the loop is clockwise. If we're using the conventional axes directions of x and y and z, then the direction of the pseudo vector of torque would be considered in the negative z direction. The green vector would represent the torque on the loop. It is in the negative z direction.